NASA has quietly classified a 1972 solar event as the closest call in the history of human spaceflight. Not a mechanical failure, not a launch accident, a storm from the sun that would have delivered a lethal radiation dose to any astronaut who happened to be in transit at that moment. Nobody was. The timing saved them. Now 53 years later, we are sending 4 people back into that same corridor, during a solar cycle that has already broken every prediction, during a peak phase that is statistically more dangerous than anything Apollo faced. The question nobody is asking loudly enough is, what happens if the timing doesn't save them this time? Stay until the end. The answer is not simple. If you genuinely enjoy what we cover here on Project Nightwatch, make sure to hit like and subscribe, because this story is only beginning, and we will be here covering every bit of it. Drop a comment below with where you are watching from, what time it is there, and your honest opinion on the timing of this mission. Now, let's get into it. Part 1. The launch window nobody is talking about. 3 days from now, 4 human beings are going to do something that no human being has done in over 50 years. They are going to leave. Not leave in the comfortable, well-documented, heavily monitored way that astronauts have been leaving since the 1970s, riding up to a station a few hundred miles overhead, still inside Earth's protective magnetic field, still close enough that an emergency return is a matter of hours rather than physics. Not that kind of leaving. The kind of leaving that only 24 people in the entire history of our species have ever done. The kind where you watch Earth shrink behind you until it is a sphere, then a disk, then a point of blue light in the black. The kind where the distance between you and every hospital, every doctor, every rescue mission, every safety net that civilization has ever built is measured not in miles, but in days. The mission is Artemis II. 4 astronauts, Reed Wiseman, Victor Glover, Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen, will launch aboard the Orion capsule on the Space Launch System rocket, execute a free return trajectory around the Moon, and splash down in the Pacific Ocean approximately 10 days later. No lunar landing on this mission, just the arc out, the flyby, and the arc back. A shakedown cruise for the hardware and the humans who will eventually attempt to land on the surface. That description makes it sound almost routine. It is not routine. And the reason it is not routine is something that the mission coverage, the launch countdowns, the astronaut profiles, the engineering achievement framing is not spending enough time on. Let us start with the magnetosphere, because everything else in this conversation connects back to it. The magnetosphere is Earth's invisible protective field, generated by the planet's molten iron outer core spinning inside a solid inner core, creating a geodynamo that produces one of the most consequential magnetic fields in the solar system. It extends tens of thousands of miles in every direction, compressed on the sun-facing side by solar pressure, stretched into a long tail on the opposite side, and it does something absolutely critical for every living thing on this planet. It deflects the solar wind. The solar wind is the constant outward flow of charged particles, protons, electrons, heavier ions, that the sun sheds continuously in all directions at speeds of hundreds of kilometers per second. Without the magnetosphere, those particles would not pass harmlessly around Earth. They would interact with the upper atmosphere, stripping it away over geological timescales. They would reach the surface, they would reach us. We know what happens to planets without magnetospheres because we have one in our own solar system as a reference case. Mars lost its global magnetic field billions of years ago, and the consequences were permanent and total. Its atmosphere was gradually eroded by the solar wind. Its liquid water surface was stripped away. What remains is a cold, irradiated, nearly airless world. The magnetosphere is not a nice feature of Earth. It is one of the preconditions for the existence of everything we know. When astronauts are aboard the International Space Station, orbiting at roughly 250 miles altitude, they are inside that field, fully inside it. The magnetosphere reaches far beyond the station's orbit, and while radiation levels aboard the ISS are meaningfully elevated compared to the surface, enough that long-duration crew members accumulate significant career dose limits, the environment is bounded, characterized, and studied with decades of accumulated data. Space medicine researchers have built an entire clinical database around ISS radiation exposure. They know what 6 months aboard the station does to the human body in terms of radiation biology, because they have measured it hundreds of times across dozens of crew members. Artemis II is going to a place where none of that data was collected. The Orion capsule will travel approximately 240,000 miles from Earth. It will cross the Van Allen belts, the donut-shaped regions of trapped radiation that girdle Earth at various altitudes, during departure and again during return. And for the majority of the 10-day mission, it will be in the translunar corridor, open space between the Earth and the Moon, outside the magnetosphere, with no deflection of the solar wind and no attenuation of the full solar energetic particle environment. The ISS sits inside a force field. Artemis II flies without one. Now here is where the timing enters the story, and why the timing is the thing that should be front and centre in every discussion of this mission. We are currently in solar cycle 25. The Sun operates on an approximately 11-year cycle of magnetic activity, winding up from solar minimum, where activity is low and the solar surface is relatively quiet, through solar maximum, where sunspot numbers peak, where solar flares fire frequently, and where the probability of major energetic particle events is at its highest. Right now, we are in or very near the peak phase of solar cycle 25, solar maximum. The worst possible phase of the solar cycle to be outside Earth's magnetosphere, and the exact phase during which Artemis II is scheduled to fly. That alone would be a significant operational context, but solar cycle 25 has not behaved the way it was expected to behave. When scientists at NASA and NOAA published their consensus forecast for this cycle, back around 2019 and 2020, they projected it would be a moderate, unremarkable cycle, similar in magnitude to the preceding cycle 24, which was itself one of the weakest cycles in a century. The forecast peak sunspot number was around 115, a manageable, well within historical norm solar maximum. What has actually happened is that solar cycle 25 began climbing faster than any model predicted and kept climbing. By 2023 it was already significantly above forecast. By 2024 and 2025, observed sunspot counts were running approximately 70% above the original predictions. The active regions that have developed on the solar surface have been larger, more magnetically complex and more eruptively productive than the cycle model suggested they would be. Last week alone, 14 M-class flares erupted from a single active region complex. One region, 7 days, 14 eruptions of moderate to significant energy. And that same region complex is going to be in a geo-effective position, facing Earth, facing the translunar corridor, facing the flight path, during the Artemis II launch window. Geo-effective positioning is a term that sounds technical, but the concept is direct. The Sun rotates. Its active regions rotate with it, sweeping across the solar disk from our perspective over a period of roughly 27 days. When an active region is on the far side of the Sun, its eruptions travel away from Earth into the outer solar system, largely harmless from our perspective. When that same region is positioned near the centre of the solar disk, when it is facing directly toward Earth, any eruption it produces sends its energy in our direction. And in the case of Artemis II, in our direction means in the direction of 4 astronauts, travelling through open space with no magnetosphere between them and whatever the Sun decides to do. The Orion capsule has a radiation monitoring system. It has a storm shelter protocol. NASA has coordinated with NOAA's Space Weather Prediction Center for real-time monitoring throughout the mission. None of that is theatre. It is serious engineering and serious planning, and it represents a genuine improvement over anything that existed during the Apollo program. We will spend considerable time examining exactly what those protections look like and what their limits are. But here is the central point that needs to be established before any of that detail matters. The question of whether Artemis II encounters a dangerous solar event during its 10-day window is not primarily a question about engineering. It is a question about timing, about whether the Sun, which does not operate on NASA's schedule, which does not pause its activity during launch windows, which has been producing multiple major events per week from a region currently aimed at the translunar corridor, decides to produce a mission-threatening event during the specific hours and days when 4 human beings are in the most exposed phase of their trajectory. 50 years of human spaceflight have taken place almost entirely inside the magnetosphere. 50 years of ISS crews, shuttle missions, Mir operations, Skylab occupancy, all of it inside the protective field, all of it at altitudes where the most dangerous aspects of the solar radiation environment are attenuated. Artemis II ends that era. The crew is going outside, and the Sun, right now, is not behaving the way the model said it would. This mission is not dangerous because of space, it is dangerous because of when it is happening. That distinction matters for everything that follows, and what follows is considerably more complicated and considerably more concerning than the official mission briefings suggest. Part 2. We're launching into a statistical spike. To understand why the timing of Artemis II is genuinely alarming to people who spend their careers watching the sun, you first need to understand what solar cycle 25 was supposed to look like, and then you need to look at what it actually looks like, because the distance between those two pictures is the entire story. Every solar cycle is measured primarily by tracking sunspot counts over time. Sunspots are darker regions on the photosphere, the visible surface of the sun, where intense concentrations of magnetic field lines have punched through the surface layer and suppressed the normal convective upwelling of hot plasma. They look like blemishes on an otherwise uniform surface. In visible light imagery, they appear as dark spots surrounded by slightly lighter penumbral regions, scattered across the solar disk in patterns that change from day to day and week to week, as new regions emerge and old ones decay. They are not cosmetically interesting. They are physically significant. Sunspots are the surface expression of enormous concentrations of magnetic energy building beneath the photosphere, and the more of them you see, the more magnetic energy is available to release in sudden, violent events. More sunspots equals more potential for flares. More complex sunspot groups where different magnetic polarities are mixed and tangled in close proximity, equal disproportionately more potential for the largest events. The relationship is not perfectly linear, and it is not perfectly predictable from sunspot counts alone, but the correlation is real enough that sunspot number has been the primary index of solar activity for over 2 centuries. Records go back to the early 1700s, giving us a dataset long enough to identify the approximately 11-year periodicity of the cycle with high confidence and to compare the current cycle against historical baselines. Solar cycle 24, which ran from roughly 2008 to 2019, was the quietest cycle in approximately 100 years. Its peak sunspot number was around 116, noticeably below the long-term average, and the cycle was characterized by relatively weak and short-lived active regions, fewer major flares than typical solar maxima, and a generally subdued energetic output. Researchers who study long-term solar behavior noted it as an outlier on the quiet end of the historical distribution. Some theorized it might represent the beginning of a prolonged solar minimum analogous to the Maunder minimum of the 17th century, when sunspot counts dropped to near zero for several decades. That did not happen. But cycle 24's weakness set a baseline expectation for cycle 25 that turned out to be badly wrong. When the consensus forecast for cycle 25 was published in 2019 by an international panel of solar physicists coordinated by NASA and NOAA, it called for a peak smoothed sunspot number of approximately 115, almost identical to cycle 24, a continuation of the quiet pattern, nothing to get excited about. Solar maximum would arrive, activity would be elevated above minimum levels but not dramatically so, and the cycle would wind down through the mid to late 2020s without particular incident. Cycle 25 had other ideas. It began climbing faster than any of the ensemble models in the consensus forecast predicted. By 2022, it was already tracking above the high-confidence upper bound of the forecast range. By 2023, the active regions developing on the Sun were producing events at rates more consistent with historically active cycles than with the quiet cycle the models had described. By 2024 and 2025, the divergence between forecast and reality had become the dominant story in solar physics, sunspot numbers running approximately 70% above the consensus prediction, with active regions of magnetic complexity, the beta-gamma-delta class configurations, appearing with frequency that had not been seen since cycle 23, which peaked around the year 2000 and was considered one of the more active cycles of the modern era, 70% above forecast. Stop and sit with that for a moment, because it is easy to process that as a dry statistical statement and miss its physical meaning. The models that professional solar physicists, using the best available data and techniques, published as their best estimate of this cycle's behavior, are off by 70% in the direction of more activity. Not a small calibration error, not a rounding difference, a fundamental miss. The Sun has been more energetically active than the experts who study it expected, and the implications of that miss extend directly to the Artemis II launch window, in ways that are not being prominently discussed. Now, and this is important, solar maximum does not mean that every day during the peak phase is a crisis. This is a common misconception that leads people to imagine the sun as some kind of continuously firing cannon during maximum years, which is not accurate. What solar maximum means is that the probability of major events is elevated, and crucially that activity tends to cluster in bursts rather than distributing evenly across time. An active region develops on the sun over a period of days to weeks, reaches a phase of peak magnetic complexity, produces multiple events in a concentrated time window, sometimes several per day, and then decays. Meanwhile, other regions are developing on different parts of the solar surface, potentially overlapping in their active phases. The result is a solar maximum characterized by episodic bursts of intense activity, separated by quieter intervals, rather than a constant high-danger environment. That clustering behavior is precisely what makes a 10-day deep space mission during solar maximum difficult to manage from a risk perspective. It is not that all 10 days carry equal risk, it is that some subset of those 10 days, potentially concentrated in a window of 1 to 3 days if the crew is unlucky with timing, could carry very high risk. And identifying in advance which days those will be is not something current forecasting technology can do with operational reliability. The flare classification system is worth understanding because the scale is not intuitive. Solar flares are classified by their X-ray intensity as measured by the GOES satellite network. C-class flares are minor events. They produce some radio interference and minor particle flux elevations, but they represent the low end of the observable flare distribution, and are typically not a significant concern for shielded spacecraft. M-class flares are moderate events, 10 times more energetic than C-class, capable of producing radio blackouts on the sun-facing side of Earth, elevated energetic particle environments, and in some cases coronal mass ejections that can disturb Earth's magnetosphere and affect satellite operations. X-class flares are major events. Each step within the X-class represents another factor of 10 in energy output. An X2 flare is twice as energetic as an X1, an X10 flare is 10 times an X1, and the scale has no theoretical upper limit. The most powerful flare in the modern monitoring era was an X28 event in November 2003. Events in that range saturated the sensors measuring them. During the weeks leading up to the Artemis II launch window, X-class flares have been occurring at a frequency of roughly 1 per week. That alone is consistent with an active solar maximum. But the 14 M-class flares from a single active region complex in 7 days, that is a concentration of event production that reflects an unusually energetically productive region. And the fact that this region is tracking toward geo-effective alignment during the mission window is not a coincidence that planners can comfortably dismiss. Coronal mass ejections add another dimension to the risk picture. A CME is a large eruption of magnetized plasma from the Sun's corona, the Sun's outer atmosphere, that travels outward through the solar system at speeds ranging from a few hundred to several thousand kilometers per second. Unlike the X-ray and ultraviolet radiation from a flare, which travels at the speed of light and arrives at Earth within about 8 minutes, a CME is a physical mass of plasma and magnetic field that takes anywhere from 1 to 3 days to travel from the Sun to Earth's orbital distance, depending on its speed. When a fast, Earth-directed CME arrives, it can compress Earth's magnetosphere, inject energy into the magnetospheric system, and produce a geomagnetic storm, the kind of event that drives aurora to unusually low latitudes, that stresses power grid infrastructure, and that temporarily intensifies the radiation environment in near-Earth space. For astronauts outside the magnetosphere, the CME arrival geometry is different. They are not inside the system that a CME compresses and disturbs, they are in the path of the plasma cloud itself. The interaction between an unprotected spacecraft and an arriving CME depends heavily on the CME's magnetic field orientation, its particle content, and the specific trajectory of the spacecraft at the time of arrival. Modelling that interaction with precision is currently not possible. The forecasting difficulty is not unique to Artemis II. It is a structural limitation of solar physics that has not been solved in the 50-plus years of space weather monitoring. Models can characterise the current solar state. They can produce probabilistic assessments of what that state implies about flare likelihood over the next 24 to 48 hours. They cannot reliably predict the timing of individual events beyond that window, and their accuracy on the 48 to 72 hour horizon is substantially lower than their 24-hour accuracy. The Sun's magnetic behaviour is inherently nonlinear. Small differences in the magnetic field configuration can produce qualitatively different outcomes, and the measurement precision required to distinguish those configurations is beyond current instrument capability. What this means for a 10-day mission launching into an active solar maximum is that the risk does not come with an attached schedule. There is no forecast that says danger window opens on mission day 4 and closes on day 7. The window is the entire mission, and the specific window that Solar Cycle 25's unexpectedly aggressive behaviour has created for Artemis II is wider and more loaded with potential than any window that has opened for a crewed deep space mission in decades. The Sun is active, yes, but the more important point, the one that should be generating more discussion, is that it becomes dangerous in bursts we cannot schedule, and the next burst could come tomorrow. It could come during launch. It could come on day 3, when the crew is at maximum distance from Earth, past the point of any realistic option to accelerate their return. That is what the numbers are actually saying, and that is what is worth paying close attention to as this launch window opens. But sunspot counts and flare frequencies are just the statistical backdrop. The foreground, the specific, active, magnetically complex region currently sitting on the solar disk and rotating toward direct alignment with the Artemis II flight path, is where the story gets genuinely specific. And specific is where it gets uncomfortable. Part 3. The sunspot facing the crew. There is a patch of the Sun right now that deserves your full attention. Not because the Sun is uniformly dangerous across its entire surface, it is not. Activity concentrates in specific regions, specific areas where the magnetic field topology becomes complicated enough to store and release enormous amounts of energy. Most of the Sun's surface at any given moment is relatively quiet. Plasma convects, granules form and dissolve, the photosphere does its thing, but certain regions, sometimes one, sometimes several simultaneously, develop what solar physicists call active region complexity, where the local magnetic field becomes so entangled that the region becomes capable of producing significant events on a frequent basis. And right now, one such region is positioned in a way that should be drawing considerably more public attention than it is receiving. Solar active regions form when strong magnetic field lines from the Sun's interior push through the photosphere, creating concentrations of flux that manifest as sunspot groups. The key variable is not just the presence of sunspots, it is the magnetic geometry of the sunspot group, specifically whether different magnetic polarities are present in close proximity and in configurations that create strong stressed field gradients. Solar physicists classify active regions using a system based on their magnetic topology. Simple, bipolar regions, a north and south magnetic polarity cleanly separated, are relatively stable. Complex regions where multiple polarities are mixed together in patterns that resist simple labeling are energetically volatile. The most dangerous classification in the standard system is designated beta gamma delta. The Greek letters describe progressively more complex levels of magnetic mixing. A beta region has simple bipolar structure. A gamma region has more complex polarity mixing that does not fit the simple bipolar pattern. A delta region has opposite polarities sharing a common penumbra, sunspots of opposite sign so closely grouped that they are essentially touching, with the magnetic field lines between them under extreme tension. A beta-gamma-delta region combines all of these features. It is large, magnetically complex, multiply-polarized, and contains regions where field lines of opposite sign are in intimate, tense proximity. The physical analogy that captures what is happening inside a beta-gamma-delta active region is a rubber band twisted multiple times in opposite directions while being held at both ends under tension. The rubber band stores potential energy in its twisted configuration. If you release it, or if it reaches its elastic limit, it releases that stored energy violently. The magnetic field in a beta-gamma-delta sunspot group is storing energy the same way, through the topological stress of oppositely directed field lines wound around each other, compressed into a small volume, continuously being refreshed by new flux emerging from below the photosphere. The region accumulates magnetic energy over days to weeks. When that energy releases when the field lines suddenly reconnect across the boundary between opposing polarities, converting stored magnetic energy into kinetic energy and radiation, that is a solar flare. The threshold at which that reconnection occurs is not well understood in predictive terms. What is known is that the probability of a major flare from a beta-gamma-delta region is substantially higher than from simpler configurations. On any given day, the 24-hour probability of an M-class or larger event from a well-developed delta region can reach 50, 60 or higher %. That is not prediction of a specific event. It is a statement about the statistical character of those configurations. They produce major events frequently, and the active region complex that has been erupting 14 times per week is organized around exactly this kind of magnetic structure. Now the geometry. The Sun rotates, carrying its active regions across the visible disk from Earth's perspective over approximately 27 days. Active regions emerge, evolve through their most productive phase, and decay over periods of days to a few weeks. The current region complex has been among the most productive seen in this solar cycle, and its rotation is carrying it toward the center of the solar disk, the point of maximum geoeffective alignment, where any eruption it produces will be most directly aimed toward Earth and toward the space between Earth and the Moon. Geoeffective position is not a binary. It is a range. A region does not become suddenly dangerous the moment it crosses a meridian line on the solar disk. Rather, as it rotates from the solar limb, the edge of the disk as seen from Earth, toward disk center, the probability that its eruptions will be Earth-directed increases progressively, peaks near disk center, and then decreases again as the region rotates past center toward the opposite limb. The window of meaningful geoeffective positioning for a major active region is roughly plus or minus 5 to 7 days around disk center crossing, a 2-week window during which that region's eruptions carry the highest probability of impacting Earth's orbital environment. The Artemis II 10-day mission window falls within this region's geoeffective phase. That is the specific geometric conjunction that elevates the solar risk for this mission above the background level of solar maximum activity. NOAA's SPACE, Weather Prediction Center, publishes daily probability forecasts for C-class, M-class and X-class flares. These are 24-hour and 48-hour probabilistic assessments, percentage likelihood of at least one event of that class occurring during the forecast period. It is important to understand what these numbers mean and what they do not mean. A 45% probability of an M-class flare in the next 24 hours does not mean there is a 55% chance the Sun will leave you alone. It means that under current conditions, nearly half of all 24-hour periods with similar observational features produce at least one M-class flare. The probability reflects the ensemble of similar solar states, not a specific prediction for this day, and it does not tell you when during the 24 hours the event will occur, how large within the class it will be, or in which direction the emission will propagate. The particle physics of how a solar flare radiation event actually reaches a spacecraft is worth walking through carefully, because the timing structure of that process is central to the crew's options if an event occurs during the mission. When a major flare fires, the first signal is a burst of electromagnetic radiation, X-rays and extreme ultraviolet photons that travels from the Sun at the speed of light and arrives at Earth's orbital distance in approximately 8 minutes. That electromagnetic burst is the first indicator an event has occurred. It produces the X-ray increase that satellites detect and that triggers the initial alert. What follows over the next minutes to hours is the energetic particle component. Protons and electrons accelerated to a significant fraction of the speed of light. By the shockwave and magnetic reconnection processes of the flare can begin arriving at Earth orbital distance anywhere from roughly 15 minutes to an hour after the flare onset, for the fastest, highest energy particles from the most powerful events. The bulk of the particle flux from a large solar energetic particle event may take 1 to several hours to reach peak intensity, as particles of varying energies and velocities arrive in sequence. A major SEP event can sustain elevated particle flux for many hours, sometimes more than a day, as the event evolves. This timing structure creates what looks like a meaningful warning window. The electromagnetic signal arrives before the particles, and the particle flux builds gradually toward peak. But this apparent warning is substantially narrowed by a phenomenon that solar physicists call the silent buildup problem. In the minutes, hours, or even days before a major eruption, there is no reliably detectable precursor signal in the active region's observable behavior that unambiguously distinguishes the pre-flare state from a state that will not produce a flare. The region sits there, accumulating magnetic tension, looking much as it did yesterday and the day before. Then it erupts. The onset of the energy release happens on timescales of seconds to minutes. The 15-minute to 1 hour window between electromagnetic arrival and particle peak is not a warning before the event. It is a countdown after the event has already begun. For the crew of Artemis II, this means the operational sequence during a major event looks like this. Sensors aboard the spacecraft and alerts from mission control indicate a significant flare has occurred. The crew has between roughly 15 minutes and, in the best-case scenario, an hour or more to implement shelter configuration before the worst of the particle flux arrives. Whether that is enough time depends on the specific event's particle acceleration efficiency, on the interplanetary magnetic field conditions between Sun and spacecraft, and on what the crew was doing when the alert arrived. It is workable for many events. It is tight for the fastest events from the most energetically productive eruptions. And it requires the crew to be prepared, trained, and in a state of readiness that can be sustained for 10 days without fatigue degrading response time. If it erupts while they are in transit, at the wrong time, on the wrong day, when the particle arrival time is faster than typical, there is nowhere to go and very little time to prepare. The physics of that scenario does not change based on how well designed the capsule is. It changes based on when the Sun decides the rubber band has been twisted far enough. Part 4. The 10-day trap. Most people, when they hear that astronauts are going to the moon, imagine that the mission looks something like an airplane trip, a journey with a clear beginning, middle and end, and the implicit assumption that if something goes badly wrong, you turn around. You come home, you land somewhere. The emergency option exists in the background as an unstated assumption, the way fire exits exist in buildings. You hope you never need them, but the knowledge that they are there changes the psychological character of the space you're in. Artemis II does not have fire exits. And understanding exactly why, not as an abstract statement but as a physical and mechanical reality, is essential for grasping what the crew is actually committing to when they strap in. The trajectory that Orion will fly is called a free return trajectory. The concept was used during Apollo, and it remains a fundamental tool of translunar mission design for a straightforward reason. It uses the moon's gravity to assist the spacecraft's return without requiring a large propulsive burn. In a free return trajectory, the spacecraft departs Earth on a path calculated so that if no major engine burn is performed at any point, the moon's gravity will curve the trajectory around the far side of the moon and redirect the spacecraft back toward Earth on a return arc. The crew gets a safe return path essentially for free in terms of fuel cost, as a consequence of the orbital mechanics of the Earth-Moon system. This is elegant and valuable engineering. It provides a safety baseline. Even in a complete propulsion failure scenario after the translunar injection burn, the crew would eventually return to Earth re-entry conditions without requiring any additional engine burns. The free return trajectory is a genuine safety feature, not a marketing claim. But here is what it does not provide: speed. The timeline of a free return trajectory is dictated by orbital mechanics, not by the urgency of events aboard the spacecraft. The arc to the moon and back takes the time it takes. There is no shortcut. There is no option to convert the trajectory into a faster return by burning more fuel, because the fuel budget for the mission is sized to execute the planned mission, the trajectory corrections, the attitude control, the burns required by the designed flight path, not to provide a reserve capable of dramatically compressing the mission timeline in an emergency. Compare this to the International Space Station. A crew member aboard the ISS who needs emergency medical evacuation, or who is aboard a station facing a critical systems failure, can board a Soyuz or Crew Dragon escape vehicle and be on the ground within approximately 3 hours of undocking. 3 hours. That fact, the 3-hour return, shapes everything about the operational character of the ISS. It is the reason long-duration ISS missions are considered medically manageable without having a physician permanently stationed on board. It is the reason the station does not carry the pharmacy required for a remote, isolated expedition. The 3-hour return is the medical backstop that allows the station to function the way it does. Artemis II's equivalent backstop in a mid-mission emergency is measured in days. If a medical emergency occurs on day 5 of the mission, when the crew is near their maximum distance from Earth, the return timeline is not 3 hours. It is the remainder of the mission arc, days of travel before re-entry becomes possible. During those days, the crew are their own doctors, their own emergency responders, their own decision makers. Mission control can advise, guide, and support, but the speed of light still takes 1.25 seconds to cover the distance between Earth and the Moon, which means real-time conversation is possible, but physical help is not. The propulsion situation is worth being specific about. The European service module attached to Orion carries the main engine and the fuel necessary for the mission's planned maneuvers. A rough estimate of the Delta-V budget, the total velocity change capability, built into the mission covers what the mission was designed to do. What it does not cover is a hypothetical abort maneuver that would punch directly across the translunar corridor toward Earth on a compressed timeline. The orbital mechanics of the Earth-Moon system require a significant velocity change to transition from the free return arc to a dramatically shorter return path. That velocity change requires fuel that the mission simply does not carry and could not carry within realistic spacecraft mass budgets. The constraint is not a design oversight. It is a fundamental feature of deep space mission architecture. This is the context in which the solar radiation risk needs to be understood. When we talk about the crew sheltering in the Orion storm shelter during a solar energetic particle event, we're talking about a shelter procedure that will be executed by people who know, with complete clarity, that if the event is larger than the shelter can adequately protect against, their options are exactly two: stay in the shelter or stay in the shelter. There is no third option. There is no flight path that gets them back faster. There is no emergency vehicle docking at the capsule. The trajectory is committed. The physics owns the timeline. The storm shelter configuration aboard Orion is a designated position within the capsule that offers the most shielding from the surrounding spacecraft structure and stowed equipment. During a radiation alert, the crew moves to this position and rearranges available mass, food stores, water containers, equipment bags around the shelter position to increase the shielding depth between the crew and the direction of particle flux. The physics of this approach is well understood. Energetic particles lose energy as they pass through matter, and the denser and more hydrogen-rich the matter, the more efficiently it absorbs the lower to moderate energy proton flux characteristic of most solar energetic particle events. Inside Orion, this configuration provides real and meaningful radiation dose reduction compared to being distributed throughout the capsule during an event. Studies of the shelter approach using radiation transport modelling suggest it can reduce dose rate by a factor that meaningfully pushes moderate events below the threshold of immediate health concern. That is genuine mitigation value, and it is the result of serious engineering thought about how to use available mass most effectively within the constraints of a spacecraft that has to be as light as possible. The Van Allen belts add a context layer to the overall mission radiation accounting. Artemis II will cross the inner and outer Van Allen belts on the outbound phase of the mission, and again on the return. These crossings are not instantaneous. They take several hours at the spacecraft's velocity, and they deliver doses that are significant relative to ISS daily average exposure rates. The belts are more intense and more variable during solar maximum than during solar minimum, because energetic solar events inject additional particles into the belt population and can temporarily inflate the belt intensity, particularly in the outer belt. The timing of belt crossings relative to recent solar events affects the dose received during transit. Cumulative dose over the full 10 days, including belt crossings, background galactic cosmic ray exposure, and any solar energetic particle events that may occur, is the quantity that mission planners have calculated against the crew's career radiation exposure limits. Those limits are set by NASA's occupational health standards and represent the agency's judgment about acceptable lifetime cancer risk increases for astronaut careers. The planned Artemis II mission should be executable within those limits under normal conditions. Under conditions involving a major solar particle event, the margin narrows sharply, and for an event in the range of the historical worst cases, the mission exposure accounting becomes genuinely problematic. Once this mission launches, the trajectory behaves like a stone thrown in a specific direction, with a specific velocity. The Moon will catch it and redirect it. Gravity will curve it home, but the time it takes, and the space it passes through, and whatever the Sun decides to do during those 10 days, those are not parameters that can be renegotiated once the launch vehicle clears the tower. This is not a mission you can turn around. It is a committed arc through space, and the Sun does not honour commitment deadlines. Part 5. The last time we tried this, we got lucky. August 4th through 9th, 1972. Write those dates down, or at the very least hold them in mind for the next few minutes, because they represent something that has never been adequately absorbed into the public understanding of human spaceflight history, and they are directly relevant to what is happening right now. Between the splashdown of Apollo 16 in April of 1972 and the launch of Apollo 17 in December of that same year, the Sun produced what remains one of the most powerful solar particle events in the history of space weather observation. Not just powerful by the standards of routine solar activity, powerful by the historical record, an event that, when modelled using modern particle transport physics and compared against the available measurements from that era, appears to have been among the most intense solar proton events of the 20th century. The event began in early August with a series of major flares from an active region that had been building in magnetic complexity over several weeks. The most intense phase produced an extraordinary flux of high-energy protons that flooded the interplanetary medium over a period of several days. Ground-based neutron monitors, instruments that detect secondary particles produced when cosmic rays and solar energetic particles interact with Earth's upper atmosphere, recorded increases that put the event firmly in the category of major solar proton events. Multiple instruments across the early space-based monitoring network registered the particle flux at levels that saturated some detectors and pushed others near their upper measurement range. When radiation physicists apply modern particle transport models to the measured fluxes from that event, and calculate what a human being would have received in the translunar corridor, outside Earth's magnetosphere, in a spacecraft with hardware typical of the Apollo Command and Service module, the resulting dose estimates range from uncomfortably high to potentially lethal, depending on assumptions about specific spacecraft positioning and the details of shielding configuration. The range of estimates in the published literature is wide, reflecting genuine uncertainty in the reconstructed particle spectrum from measurements that were not designed with human dose assessment in mind. But the consensus framing among space medicine researchers who have studied the event is that astronauts in transit during August 1972 would have received a radiation dose representing a serious medical event, likely incapacitating, potentially fatal at the higher end of the plausible estimates, and certainly well above any occupational safety threshold in any framework that has ever been applied to human spaceflight. The crew of Apollo 16 had returned to Earth on April 27th. The crew of Apollo 17 would not launch until December 7th. Between those two missions, the translunar corridor was empty of human beings when the Sun fired one of its most powerful salvos in recorded history. That timing was luck, not planning, not superior engineering, not advanced forecasting that chose the safe window between the dangerous missions. The Apollo program did not have operational space weather forecasting. The Space Weather Prediction Center, that today provides continuous monitoring and probabilistic forecasts, did not exist. Solar monitoring capability in 1972 consisted of ground-based observatories, some early satellite instruments, and radio monitoring networks, adequate for detecting that a major event was in progress, not adequate for providing advance warning that would have allowed mission planning decisions to shift around the event. If Apollo 16 or Apollo 17 had been on a translunar trajectory in early August 1972, they would not have received a meaningful warning before the particle flux began rising around their spacecraft. NASA's post-analysis of the August 1972 event has led to its classification in various technical and historical documents related to space radiation risk, as a reference case for the worst-case solar scenario in the context of human spaceflight. Not a model worst case developed theoretically, an actually observed event, documented by real instruments, that we know the Sun is capable of producing because we watched it happen. Whatever the exact dose estimates contain in terms of uncertainty, the particle fluxes were measured. The event was real. The Sun did this. There is an important and sometimes overlooked detail about the exposure comparison between an astronaut conducting a spacewalk and one inside the spacecraft during such an event. During a solar energetic particle event, an astronaut in a spacesuit performing an EVA is exposed to a dramatically higher dose than one inside the spacecraft. Because the spacecraft structure, even the relatively thin aluminum of the Apollo capsule or the Orion capsule, provides meaningful shielding against the bulk of the proton flux, while a spacesuit provides essentially none. No Artemis II EVAs are planned, which removes the worst-case exposure scenario from the mission profile. But the interior spacecraft dose during a major event is still the quantity that matters, and the Apollo Command Module's shielding was modest by modern spacecraft standards. What did NASA learn from the August 1972 event? Significant lessons. The event drove the development of more sophisticated radiation monitoring instruments for subsequent programs. It informed the design of the radiation warning system architecture that evolved through the shuttle era and into the ISS program. It established the importance of real-time coordination between solar monitoring agencies and human spaceflight operations centers. The Orion capsule's storm shelter design, the NOAA coordination protocols for Artemis missions, the personal dosimetry system the crew will wear, all of it has intellectual lineage connecting back to the recognition, after August 1972, that humans in deep space are genuinely vulnerable to solar radiation events in ways that demand operational preparation. None of that learning changed the fundamental physics. The sun that produced the August 1972 event is the same sun that the crew of Artemis II will be flying around. The nuclear fusion process at its core, the convection zone dynamics that drive the magnetic cycle, the active region formation and flare production mechanisms, none of that has changed. What has changed is that solar cycle 25 is more active than solar cycle 20, as measured by any comparable metric. The cycle that produced the August 1972 event, solar cycle 20, was itself considered a moderately active cycle by historical standards. Solar cycle 25 has been running above that baseline. Orion is better shielded than the Apollo command module. It has better radiation monitoring. The mission has better forecasting support. These improvements are real and they are not trivial, but they are improvements on a problem that was not solved in 1972 and has not been solved in the 50 years since. The fundamental vulnerability, human beings in deep space, outside the magnetosphere, during a period of elevated solar activity, is the same vulnerability. The engineering has improved the margin. It has not eliminated the risk category. What the Apollo program demonstrated is that you can send human beings through the translunar corridor and bring them home safely. What it also demonstrated in the silence between Apollo 16 and Apollo 17, in the empty corridor through which the August 1972 event roared without casualties, is that safe outcomes are not guaranteed by engineering capability alone. The Apollo astronauts who survived deep space did so because the physics worked out for them at each specific moment of maximum exposure. The August 1972 event chose an empty corridor. We did not solve the danger. We simply did not encounter it at the wrong time. And now we are going back with 4 people into a sun that is statistically more active than the one Apollo faced. The next question is whether what we have built since 1972 is adequate for the conditions that solar cycle 25 is presenting right now. The answer to that question has a lot of technical nuance, and some of that nuance is not reassuring. Part 6. Radiation isn't the same outside Earth. Here is something that sounds simple, but has genuinely significant implications for how we should think about the Artemis II mission. The radiation environment that the crew will inhabit for 10 days does not have a close analogue in any database of human health data ever collected in the history of spaceflight. The data we have is real, it is extensive, and it is scientifically valuable. But it comes from a different place, and the difference between the place where the data comes from and the place where the crew is going is not a fine distinction. It is a fundamental one. Let us map out what space radiation actually consists of, because the term covers several distinct physical phenomena that interact with human biology in different ways and carry different levels of understood and uncertain risk. The first and most familiar component is the trapped radiation of the Van Allen belts, the regions of energetically charged particles held in place by Earth's magnetic field at altitudes ranging from roughly a few hundred miles out to tens of thousands of miles. The inner belt is dominated by protons, the outer belt by electrons, and both are regions of elevated particle flux relative to the ambient interplanetary environment. Every crewed mission that goes beyond low Earth orbit must transit these belts, and Artemis II will cross them twice. The belt environment is the most thoroughly characterized component of the deep space radiation picture, because it sits close enough to Earth that it has been monitored by dozens of spacecraft over more than 60 years. It is not a trivial exposure, but it is a calculable and bounded one. The second component is solar energetic particles, the acute event-driven radiation from solar flares and coronal mass ejections. This is the component we have spent most of our time on because it represents the most dynamic and least predictable risk for Artemis II given the current state of the Sun. SEP events range enormously in intensity, particle energy spectrum and duration. They are the primary reason that solar maximum timing matters for human deep space missions, and they are the component for which the shelter protocols and monitoring systems are specifically designed. The biological consequences of acute SEP exposure depend on the dose rate and duration. At high enough dose rates, radiation sickness symptoms can appear within hours. At extreme dose rates, the acute radiation syndrome that poses direct mission threat can develop rapidly. At lower doses, the primary concern shifts to longer-term cancer risk. The third component is galactic cosmic rays, and this is the one that operates quietly in the background, drawing less attention than solar storms but carrying implications for human health that extend beyond any individual mission. Galactic cosmic rays are not solar. They come from outside the solar system, from the energetic remnants of stellar explosions, from the acceleration mechanisms associated with neutron stars and other extreme astrophysical environments throughout the galaxy. They arrive at Earth's orbital neighbourhood from essentially all directions simultaneously, at a range of energies that spans many orders of magnitude. The lower energy portion of the galactic cosmic ray spectrum is partially attenuated during solar maximum. The stronger solar magnetic field and expanded heliosphere push back against low-energy cosmic rays, slightly reducing their flux in the inner solar system. The high-energy portion is barely affected. The high-energy galactic cosmic ray component is what makes deep space radiation genuinely different from anything representable in Earth-based testing or ISIS data. These particles, primarily high-energy protons and heavier ions, carry enough energy that they penetrate essentially any shielding thickness that a spacecraft could realistically carry. Worse, when a high-energy heavy ion passes through dense shielding material, it can produce secondary particles through fragmentation reactions in the shielding material itself, potentially increasing the biological dose on the other side compared to no shielding. This phenomenon, called the shielding plateau and secondary particle problem, means that the straightforward intuition of adding more shielding to protect against high-energy cosmic rays is actually counterproductive above a certain shielding thickness for the highest energy component. For a 10-day mission like Artemis II, the galactic cosmic ray contribution is a secondary concern to the acute SEP risk. 10 days of background cosmic ray exposure in the translunar corridor is a real dose increment, and it contributes to the total mission dose accounting, but it does not by itself push the mission into unsafe territory for a crew operating within career limits with radiation dose management. The galactic cosmic ray problem becomes urgent on timescales of months in the context of Mars missions. For Artemis II, it is the background term in the dose equation, not the leading term. But here is the deeper issue that galactic cosmic rays illustrate about the radiation data gap. The ISS, where almost all of humanity's accumulated data on human beings in the radiation environment of space has been collected, orbits inside the magnetosphere. The galactic cosmic ray flux at the ISS is attenuated by the same magnetospheric shielding that deflects solar wind. The SEP environment at the ISS is filtered by the same field that protects the surface. The entire 50 years plus corpus of human data on radiation in space, the epidemiological studies of astronaut health outcomes, the biological sample analysis, the dosimetry records, the radiation-induced health effect assessments, was collected in an environment where the most energetic and penetrating components of the space radiation field were already partially removed before they reached the subjects. The crew of Artemis II will be the first human beings in over 50 years to accumulate radiation exposure data in the actual, unfiltered translunar radiation environment, with the monitoring sophistication to capture that data meaningfully for research purposes. That is a significant scientific contribution of the mission. It is also an honest description of an epistemic gap. The safety standards, the dose limits, the biological risk models that govern the mission were developed using data from a different radiation regime. The scientists who built those models are aware of this. They have extrapolated carefully, used the best available physics to bridge the gap, and produced the best possible estimates, but they are estimates. And the Sun, this month, is producing conditions that are testing those estimates at an unusually demanding point on the input distribution. The uncertainty in biological tolerance thresholds matters here. Radiation protection standards are built around risk models, statistical relationships between dose and health outcome probability that themselves carry uncertainty ranges. The specific biological effectiveness of the galactic cosmic ray heavy ion component, for example, is not well characterized in human data at all, because humans have never been exposed to it in appreciable quantities. The relevant experiments use cell cultures, animal models, and accelerator-based ion beam exposures that approximate but do not perfectly replicate the natural radiation field. The uncertainty factors applied to account for this gap are not small. They represent a genuine acknowledgement by the radiation protection community that we are working at the edge of what the data allows us to say. The crew of Artemis II will wear dosimeters, the spacecraft will carry active radiation monitors, the data collected will advance the field. In a real sense, the crew is not just flying to the moon, they are generating the dataset that the next generation of mission planners will need to make better decisions about human deep space health. The price of generating that dataset is accepting that the current models, for all their sophistication, are partially extrapolated into territory where the extrapolation has not yet been validated by measurement. We are leaving the dataset that everything we know is based on. What we find on the other side will matter for every human being who follows. Part 7. Inside Orion's Storm Shelter. It is worth spending time inside the Orion capsule, not in the abstract language of mission profiles and system specifications, but in the physical, spatial, human reality of what those 4 people will actually experience if the Sun fires a significant event during their transit. Because the engineering is genuinely good, and the systems are genuinely better than anything that existed during Apollo. And none of that changes the fact that what is available to protect those 4 people in the most demanding scenario is a shelter that was built to the best possible compromise between mass, volume, and physics inside a vehicle that had to launch on a rocket. Let us start with the capsule itself. Orion's crew module is roughly 16.5 feet in diameter, larger than Apollo, designed to support 4 crew members for missions of up to 21 days in the lunar vicinity. The interior volume provides more space than Apollo for crew positioning and equipment stowage, but it's still a vehicle interior, not a room. 4 people sharing that space for 10 days are in close quarters. The European service module attached to the aft end of the crew module provides propulsion, power, life support, consumables, and a significant mass of hardware and structure that contributes passive radiation shielding for the crew positioned at the forward end of the vehicle. The storm shelter configuration takes advantage of several features of the capsule design and mission consumable manifest. During a radiation alert, the crew transitions to the shelter position, an area within the capsule that benefits from the maximum available shielding from surrounding hardware. The cabin's water storage, a significant mass of hydrogen-rich material, is positioned around the crew to increase shielding thickness. Food packages, equipment bags, and other stowable items are rearranged to add additional mass between the crew and the primary radiation direction. The service module, left in its normal aft position, provides shielding from particles arriving from that direction. The overall configuration creates what radiation engineers call an optimized shelter position, not uniform spherical shielding, but directionally optimized shielding that reduces the flux from the most significant exposure directions. Water is particularly effective as a radiation shielding material for the energy range of most solar energetic particle events because of its high hydrogen content. Protons, which make up the dominant particle species in most SEP events, lose energy efficiently through interactions with hydrogen atoms, through a process of Coulomb scattering that transfers proton kinetic energy into ionization of the water molecules. The thicker the water layer, the more proton energy is deposited in the shielding material rather than in the crew. Orion's water storage is a deliberate part of the shelter design, not an incidental coincidence that the mission carries water. The radiation monitoring system aboard Orion is meaningfully more sophisticated than anything that flew on Apollo. The crew wears personal dosimeters, electronic devices that measure and record dose rate in real time, giving both crew and mission control continuous information about individual exposure levels. The capsule carries active radiation detectors that characterize the particle flux environment around the spacecraft, not just total dose, but information about particle energy spectra that allows better comparison against model predictions and better assessment of event severity as it evolves. All of this data streams to mission control, where a team that includes space weather specialists monitoring the NOAA data feeds can track both the external solar conditions and the crew's exposure simultaneously and in real time. The communication advantage of lunar distances compared to planetary mission distances is relevant here. Light travel time between Earth and the Moon is approximately 1.25 seconds, essentially instantaneous for conversational purposes. Mission Control can monitor solar events, consult with NOAA forecasters, assess particle flux trends, and communicate guidance to the crew without the communication delays that will characterize future Mars missions, where one-way signal delays will reach 20 minutes or more. For Artemis II, the control team and the crew are effectively in real-time contact throughout the event response, which is a significant operational advantage. But the alert timeline has a structural limitation that no communication advantage fully resolves. NOAA's primary solar event detection capability relies on GOES satellite X-ray sensors for initial flare detection, and on the LASCO coronagraph aboard SOHO and other instruments for CME detection and tracking. The GOES X-ray detection of a flare occurs essentially simultaneously, with the flare's electromagnetic radiation arriving at Earth 8 minutes after the flare initiates on the Sun. The alert reaches Mission Control and the crew within seconds of GOES detection, which means the crew's notification of a significant solar event occurs approximately 8 minutes after it starts. The particle flux from the most energetic events begins arriving at Earth orbital distances roughly 15 to 30 minutes after the initial electromagnetic burst, for the fastest accelerating events. That gives the crew a window of 7 to 22 minutes between notification and the beginning of significant particle flux arrival, assuming notification happens immediately upon X-ray detection and the particles arrive at the fast end of the distribution. In practice, the window may be longer for many events. The bulk of the dangerous flux in most SEP events takes 1 to several hours to develop to peak intensity, and the early particle arrival is often from the highest energy, lowest flux end of the spectrum rather than the high flux phase. But the emergency shelter implementation needs to be executable in the available window, with margin, even under the least favourable circumstances. NASA's training for this scenario accounts for it, and the shelter configuration has been exercised in simulation under timed conditions. That preparation is real. The psychological dimension of shelter occupancy deserves more attention than it typically receives in mission documentation. Consider what it actually involves. 4 highly trained, extremely competent professionals confined to a small designated area within an already small vehicle, listening to radiation monitors, receiving data feeds about particle flux levels, knowing with complete clarity that the event will last as long as the Sun decides it lasts, and that there is nothing they can do to accelerate its end or change their trajectory. The cognitive and emotional load of that experience, not for minutes but potentially for hours, is not a trivial variable in crew health and decision-making. NASA's astronaut selection and training programs build resilience and equanimity specifically for high-stress waiting scenarios, but the interior experience of a shelter event on the Artemis II mission will be genuinely demanding in ways that no simulation fully replicates. It is not a bunker. A bunker implies massive passive shielding against the full range of threat scenarios. The Orion storm shelter is a carefully optimized compromise between the physics of radiation protection, the mass budget of a spacecraft, and the human factors of a crew occupying that shelter for hours. For the events that characterize the majority of solar maximum activity, it provides meaningful protection that keeps the crew within acceptable dose limits. For the extreme end of the solar event distribution, the scenarios that look like August 1972 or worse, the shelter provides meaningful mitigation, not immunity. And the active region currently facing the translunar corridor is not a moderate activity region. It is the region that produced 14 events in 7 days. What it will do during the 10-day Artemis II window is a question that the storm shelter was designed to handle, and a question that nobody can answer in advance. Part 8. The forecasting problem nobody solved. There is a distinction in solar physics that most people outside the field never encounter, but that is absolutely central to understanding the risk picture for Artemis II. The distinction is between prediction and detection. It sounds like a subtle difference. It is actually the difference between a warning system and a news report. Prediction means knowing that something is going to happen before it happens, with enough lead time to act on that knowledge. Detection means observing that something is happening after it has already begun, with enough information to characterize the event and respond to it. Modern space weather capability is extremely good at detection. It is significantly limited at prediction. And for astronauts in the translunar corridor during a solar maximum, The operational difference between those two capabilities is not academic. It is the difference between being in shelter before the particles arrive and being in shelter while they are already arriving. The core physical reason that solar flare prediction is so difficult is the nature of magnetic reconnection, the process that converts stored magnetic energy into the kinetic energy and radiation of a solar flare. Magnetic reconnection occurs when oppositely directed field lines in close proximity are pushed together. Their topology suddenly restructures, and the stored energy in the field configuration releases in a burst. The initiation of this process is a threshold phenomenon. The system can build toward reconnection over hours to days, exhibiting increasing magnetic complexity and energy storage, and then reconnection occurs when the configuration crosses a critical threshold that is determined by the three-dimensional topology of the magnetic field in the active region at scales smaller than current measurements can fully resolve. There is no measurable quantity, no precursor signal that has been validated in operational forecasting that reliably announces the approach of the reconnection threshold in advance. The active region looks complex. It has looked complex for several days. Something has been building, and then, on a timescale of seconds to minutes, the energy releases. The transition from the pre-flare state to the eruption state happens faster than any observation cadence can capture as a warning, and the physical trigger, the specific magnetic configuration that crosses the threshold, is smaller than any instrument currently deployed can resolve. This is not a technology problem that better instruments alone will solve, though better instruments will help. It is a fundamental property of a dynamical system near a bifurcation point, a state where the system is sensitive to small perturbations that push it into qualitatively different behaviors. The Sun is not hiding its state from observation. It is in a state where the macroscopic observable properties do not uniquely determine which of many possible future states the system will transition into. NOAA's Space Weather Prediction Center operates on a nowcasting model. Every day, multiple times daily, forecasters examine the current solar imagery, magnetograms, visible light imagery, extreme ultraviolet imagery from the Solar Dynamics Observatory, coronagraph data from SOHO and stereo, and produce probabilistic forecast statements for flare activity over the next 24 and 48 hours. These forecasts are genuinely useful. They are significantly better than random, and they capture the elevated probability signal associated with beta-gamma-delta active regions effectively. The 24-hour forecasts have meaningful skill when validated against historical datasets. The 48-hour forecasts have lower skill but still carry information. Beyond 72 hours, the skill of probabilistic flare forecasts drops toward the level where they are providing marginal additional value over climatological base rates. The coronagraph provides detection capability for coronal mass ejections that is somewhat different from flare forecasting. Once a CME is launched, its trajectory and speed can be tracked in coronagraph imagery, and arrival time at Earth can be estimated within a window of plus or minus several hours, typically with a 1 to 3 day lead time from launch to Earth impact. This is useful for ground-based infrastructure management. Power grid operators, satellite operators, and aviation route managers can use CME tracking to prepare for geomagnetic storm conditions. For astronauts in the translunar corridor, it provides confirmation that a major CME event has occurred and rough timing for when the plasma cloud will interact with their position. But the CME detection window assumes the CME has already left the Sun. Detection begins after the event initiates. There is no equivalent to earthquake early warning, where seismometers can detect the fast-moving pressure wave that precedes the slower, more destructive shear wave. CME detection is more like looking out the window after the storm has already started and using the radar to track where it is going. The practical consequence for mission operations is that the crew and mission control will always be in a response posture during a solar event, not a preparation posture. The monitoring systems detect the event as quickly as the physics of observation allow, which is essentially in real time, 8 minutes after the flare on the Sun via the X-ray sensors. The alerts go out immediately. The crew implements the shelter protocol. All of that can be optimized through training and preparation to minimize the response time. But the first thing that happens in a major solar event, from the perspective of the Artemis II crew, is not a warning that something is about to occur. It is a notification that something has already occurred and that the particle environment around their spacecraft is going to change. There have been notable cases in the history of space weather forecasting where the system worked well, and cases where it missed. The March 1989 geomagnetic storm, which knocked out the Hydro-Quebec power grid serving millions of people, occurred at a time when the forecast capability to predict its severity was limited. The July 2012 extreme solar storm, which produced a CME that some analyses suggest would have rivaled the Carrington event had it been Earth-directed, missed Earth by a matter of days in orbital geometry, not because of prediction that allowed avoiding it, but because the geometry was favourable and the event was recognised for what it was primarily through retrospective analysis. The honest statement is this: we do not predict solar storms in the sense of knowing before they begin that they are about to occur. We watch them after they begin, characterise them as quickly as the physics of propagation and observation allows, and respond to what is already in motion. For a crew in a spacecraft the size of a large car, 250,000 miles from Earth, during a solar maximum that is running 70% above forecast, the word response, rather than preparation, captures the operational reality more accurately than the confident language of mission briefings suggests. And the forecasting gap, the window between when a major event begins and when the crew can be fully in shelter, is the window that the sun does not have to respect. Part 9. The Superflare Window Hypothesis. Every operational space weather forecast issued by NOAA's Space Weather Prediction Center is built on deterministic solar physics and empirical statistics. It is based on direct observation of the sun's current state, historical flare rates for observed active region configurations, and ensemble models that represent the range of possible near-term outcomes. This is how you build a forecasting system that can be evaluated, validated, improved, and held accountable. It is the mainstream, peer-reviewed, operationally deployed approach. It is the approach that NASA uses for mission planning. It is science. But there is another tradition of solar research, longer period, pattern-based, statistically exploratory, that sits outside the operational mainstream and that generates, periodically, claims about structured risk windows that exceed what the current solar state alone would predict. These claims are scientifically contested. They are not part of operational forecasting. They are not incorporated into NASA mission risk assessments. And they are worth discussing clearly and honestly, with those caveats explicit, because they represent a genuine thread of scientific inquiry into solar behaviour that has not been definitively disproven, and because the question they are asking, whether extreme solar events cluster in structured temporal patterns above and beyond solar cycle phase, is a real scientific question that remains open. The research tradition this connects to goes by several names, but the underlying concept involves looking at the historical record of solar activity, sunspot counts extending back through the telescopic era to the early 1600s, and isotopic proxy records extending further back through ice cores and tree ring analysis, and identifying periodicities and patterns beyond the 11-year Schwabe cycle. The Schwabe cycle is the dominant, well-established periodicity, but researchers examining longer time series have proposed a number of additional modulations. The roughly 80 to 100-year Gleisberg cycle, which appears to modulate the amplitude of successive solar maxima, the roughly 200-year Suess de Vries cycle, and various other proposed periodicities at different timescales that different research groups have claimed to identify in the proxy data. The hypothesis that connects most directly to the Artemis II concern goes roughly like this. If longer solar cycles modulate the probability of extreme events, in addition to modulating average solar activity, then there should be identifiable phases within the longer cycles, periods of perhaps years in duration, where the probability of truly extreme solar events well above the typical solar maximum level is statistically elevated. These have been called variously grand maximum phases, superactivity windows, or in the more dramatic popular presentations, superflare windows. Researchers working in this tradition sometimes claim that certain solar behaviour patterns, including unusually fast cycle ramp-up, unusually high peak activity, and specific characteristics of active region development, can be indicators that a cycle is positioned in a high probability extreme event phase of a longer modulation. Solar cycle 25's faster than predicted ramp-up and significantly above forecast peak activity are, in this framing, potentially consistent with such an indicator. The skepticism from the mainstream solar physics community is substantial and largely justified. The fundamental problem with this research tradition is the base rate challenge. Truly extreme solar events, the kind of events that would constitute a super flare in any meaningful sense, are rare enough that the historical record contains very few confirmed examples with reliable intensity characterization. Identifying statistical clustering in a dataset of rare events requires either a very long record, very careful statistical methods, or both, and the methods used by some researchers in this tradition have been challenged on both counts. The predictive skill of proposed long-cycle models, when tested against out-of-sample data, has not demonstrated operational reliability. If a model cannot consistently predict what happened in the data that was not used to build it, the pattern it identifies may be a consequence of fitting noise rather than a real physical signal. There is also a physical mechanism problem. For a long-period solar cycle to genuinely modulate extreme event probability, there should be a physical process that explains the modulation, some aspect of solar interior dynamics or field evolution that creates conditions favourable to extreme events at specific phases of the longer cycle. While speculative mechanisms have been proposed, involving the dynamics of the tachocline, the layer between the radiative and convective zones of the Sun where the magnetic cycle is generated, none has reached the level of quantitative development and observational confirmation required for scientific consensus. What this means practically is that, if you ask the Space Weather Prediction Center whether solar cycle 25 is in a superflare window, you will not get an affirmative answer, because the concept is not part of operational models, and the evidence for it does not meet the standard required for incorporation into safety-critical decision-making. But the question itself is not illegitimate. The Sun has produced events that substantially exceed typical solar maximum activity, the August 1972 event, the November 2003 is-28 flare, the solar particle events of September 1989, and reaching further back the Carrington event of 1859. These events are real, they are documented. The Sun is physically capable of them. Whether their occurrence clustering reflects structured temporal patterns or represents the tail of a random distribution is a scientific question that proxy records do not yet clearly resolve. What is not a matter of much uncertainty is that solar cycle 25 has exceeded predictions. The models that the mainstream community published as their best estimate of this cycle were wrong in the direction of underestimating activity. That does not validate the superflare window hypothesis, but it is honest to acknowledge that the confidence interval around solar maximum forecasting is wider than the consensus forecast presentation sometimes suggests. The Sun has surprised the modelers before in this cycle in the direction of more activity. The hypothesis that proposes structured risk windows above the solar cycle baseline is unproven. The observation that we are in an unexpectedly active cycle, producing X-class flares weekly and major active region complexes of beta-gamma-delta classification, is current observational fact. For the Artemis II crew, the distinction between proven hypothesis and observed reality is somewhat academic. Whether the heightened activity of solar cycle 25 reflects a structured long-period modulation or a statistical run above average is less important than the operational reality that the activity is happening. It is above the level that was planned around, and the crew is launching into it. The superflare window debate belongs to the literature. The active region on the solar disk is on the monitoring screens right now. Part 10. The Comet Convergence. Before we get to the part of this story where we talk about what comes after Artemis II, the larger context of where human spaceflight is heading, and what the solar environment means for that trajectory, there is one more piece of the current picture worth addressing. It requires careful framing. It involves real observations, a speculative hypothesis that is genuinely contested, and a temporal coincidence that is less significant than it is interesting, in that order. A comet has been tracked by observatories and is confirmed in the catalogue of known solar system objects. Its designation is C/2026A1, discovered in January of 2026 as the designation system implies. Its orbital trajectory brings it to perihelion, its closest approach to the Sun, at a distance that places it within or very near the solar corona, the Sun's outer atmosphere. This makes it what solar astronomers call a sungrazer. Sungrazers are not exotic rarities. The Kreutz group, a family of sun-grazing comets that are almost certainly the fragmented remains of a large parent body that broke up perhaps 1,000 years ago, have been observed transiting the solar corona by the SOFO spacecraft on hundreds of occasions since SOBO's launch in 1995. Many of them are small objects, ranging in size from a few meters to a few hundred meters, that evaporate completely in the extreme environment of the corona, producing brief brightness spikes in SOHO's LASCO coronagraph imagery before disappearing entirely. Larger sun grazers survive perihelion and continue on their return trajectory, but the perihelion passage through the corona is a dramatic and physically extreme event regardless. C/2026 A1 is estimated to be a moderately sized object, large enough to potentially survive perihelion and be visible in coronagraph imagery during its solar approach. Its perihelion timing falls within or close to the Artemis II mission window. This is the temporal coincidence that has generated discussion in the space weather community, and in the online spaces where solar observers and mission watchers track these things. Now, the speculative part. There is a hypothesis, not an established result, not a mainstream model, but a recurring idea in the literature on solar-comet interactions, that under certain conditions, a comet's interaction with the solar corona could influence local magnetic field topology or trigger plasma instabilities in ways that might affect flare probability in nearby active regions. The proposed physical mechanism sometimes invoked involves the concept of critical ionization velocity, the speed at which a neutral gas or vapor moving through a magnetized plasma experiences a sharp increase in ionization, creating localized currents that could in principle perturb local field structures. A comet sublimating and depositing material into the corona could, in this framework, create a localized ionization event that perturbs the coronal magnetic field. The scientific status of this idea is that it is unconfirmed and largely unsupported by observational evidence. Multiple studies have examined coronagraph imagery from SOHO and other instruments looking for correlations between Kreutz group sungrazer transits and subsequent solar flare activity in nearby regions. The statistical results do not demonstrate a significant correlation. The Sun produces flares constantly during solar maximum, and the apparent coincidence between a sungrazer transit and a subsequent flare is likely to reflect the base rate of flare activity rather than a causal connection. The solar physics community's consensus position is that cometary interactions with the corona do not measurably affect flare probability, and NASA does not include cometary influences in its solar risk models for mission planning. Having said all of that clearly, why mention it? Because the intellectual honesty of a conversation about what we do and do not know requires acknowledging the boundaries of the mainstream models, not just their outputs. NASA's models don't include cometary influence, because the evidence for such influence is not compelling at current measurement sensitivity. That is the right reason to exclude it. It does not preclude the possibility that the models are missing something. Most of the time, when something is excluded from a model, because the evidence doesn't support including it, that exclusion is correct. Occasionally, excluded effects turn out to matter. The history of physics includes examples of both. What the comet convergence illustrates most usefully is not a specific additional risk mechanism. It is a structural point about the character of complex risk situations. When multiple independent factors, the solar cycle phase, the specific active region activity, the mission trajectory geometry, and now an independently moving astronomical object, happen to align in the same narrow time window, the situation has a character that is qualitatively different from a situation where those factors are distributed across time. Not because the coincidence is causal, not because the comet is going to trigger a superflare, but because the concentration of independently elevated risk factors in a single window is precisely how complex systems produce outcomes that are harder to reason about in advance. Three unrelated systems, the Sun, the spacecraft, and the comet, share the same calendar. That shared calendar is not evidence of anything beyond the universe's complete indifference to human scheduling. The comet's orbit was determined billions of years ago by gravitational dynamics that predate not just the Artemis program but the entire history of life on Earth. The solar cycle was not calibrated to launch windows. The coincidence is just a coincidence. But it is the kind of coincidence worth keeping in mind as we turn to what the Artemis program is actually trying to accomplish, and what the solar environment means for that ambition over the decades to come. Part 11. Space weather is becoming a human problem. For most of the history of the space age, the community of people who woke up every morning and worried about what the sun was doing was a relatively small and specialized group. Satellite operators, power grid engineers, airline dispatchers managing polar routes, GPS accuracy specialists, and the researchers who studied all of the above. Space weather was an infrastructure problem, a business continuity problem, occasionally a significant economic problem when major geomagnetic storms damaged transformers or degraded satellite systems. But it was, fundamentally, a problem about hardware, about systems, about things that could be replaced, repaired, rerouted, or restarted when the storm passed. Artemis II changes the category of the problem. When the hardware that space weather needs to protect is human beings, when the consequences of an inadequate response are not a damaged satellite or a disrupted power grid, but a medical emergency in a spacecraft. 250,000 miles from the nearest help, space weather becomes a problem of a qualitatively different kind. It becomes a problem of human survival. And that transition from infrastructure risk to human survival risk is not just a difference in scale. It is a difference in the entire framework of acceptable response options. For infrastructure, acceptable response includes damage tolerance. The understanding that some fraction of events will cause some degree of harm that is economically acceptable relative to the cost of preventing it. Power grids have insurance. Satellites have replacements. The economic calculus of risk management for infrastructure allows for loss as part of the optimization. Human spaceflight does not work this way. You cannot write a replacement into the budget line for the crew of Artemis II. The Artemis program is explicitly designed not as a one-off return to the Moon, but as the beginning of a sustained human presence beyond low Earth orbit. Artemis II is the crewed test flight. Artemis III is the planned first lunar landing since Apollo 17. Subsequent Artemis missions will build toward the Gateway, a small space station in lunar orbit that will serve as a staging point for surface missions and toward a permanent human presence at the lunar South Pole. The timeline extends into the 1930s. The mission cadence is intended to increase significantly over the coming decades. More missions means more crew members in the deep space radiation environment. More time beyond the magnetosphere means more total exposure accumulated across the human spaceflight program. For Mars, the implications scale dramatically. A crewed Mars mission, currently targeted by various agencies and commercial entities for some time in the 1930s or early 2040s, would involve transit phases of 6 to 9 months in each direction, entirely in interplanetary space, with no magnetospheric protection and no practical abort option after departure. The total radiation exposure for a 3-year Mars mission would exceed anything any human has experienced in spaceflight history. The solar energetic particle risk that occupies a critical but bounded role for a 10-day lunar mission becomes a continuous, multi-year operational concern for Mars. The galactic cosmic ray background, manageable as a 10-day dose, accumulates to levels that push against biological tolerance thresholds over a 3-year mission. Space weather is becoming the dominant constraining factor for human expansion beyond Earth's magnetosphere. This is not a statement about technology failing to keep up. It is a statement about the physics of the environment that anyone leaving the magnetosphere enters. The Sun produces what it produces. Galactic cosmic rays arrive from directions that cannot be predicted or deflected by any shielding system currently practical for a spacecraft. The biological effects of chronic radiation exposure in deep space are not fully characterized. The engineering solutions for deep space radiation protection are expensive, mass-heavy, and still limited against the highest energy component of the cosmic ray spectrum. The infrastructure investment that the space weather forecasting community needs to support the coming era of human deep space presence is substantially larger than what currently exists. More L5 observation platforms, spacecraft positioned at the gravitational balance point trailing Earth in its orbit, would provide solar observations with a viewing geometry that offers earlier warning of active region development than the current L1 assets. Better computational resources for ensemble modelling would improve probabilistic forecast skill. Dedicated space weather early warning sensors in the translunar corridor itself, rather than relying solely on near-Earth assets, would reduce the delay between event detection and crew notification. These investments are being discussed. Some are in development. None are in place for Artemis II. The more fundamental question, the one that Artemis II begins to push toward an answer, is whether human biology is compatible with the radiation environment of the routes we need to travel to reach the places we want to go. The solar energetic particle events that represent the acute risk for Artemis II are individually survivable in most cases, with adequate shielding and protocols. The cumulative dose of a multi-year Mars mission is a harder problem. The galactic cosmic ray component that penetrates everything we can practically launch is the hardest problem. Artemis II is the first measurement in a dataset that needs to be much, much larger before we can honestly say we know what we are asking of the people we send beyond the magnetosphere. Space weather has been a satellite problem for 60 years. Beginning 3 days from now, it becomes a human problem in the most direct and irreducible sense. And the question of how we handle that transition, technically, medically, institutionally, ethically, will define the character of the era of deep space human presence that Artemis II is designed to open. Part 12. AI just changed solar prediction. The forecasting problem described in Part 8, the inability to predict when a solar flare will initiate, the detection not prediction character of current space weather capability, is not a problem that the scientific community has accepted as permanently unsolvable. There is active research pushing against this limitation from multiple directions, and one of the most significant recent developments in that research involves machine learning applied to the analysis of solar magnetic field imagery. It is genuinely promising work. It is also work that has not yet reached the operational threshold that would meaningfully change the risk picture for Artemis II. The basic approach of machine learning applied to solar flare prediction works like this. The Solar Dynamics Observatory, launched in 2010 and operating continuously since, produces high-resolution, high-cadence imagery of the sun's surface in multiple wavelengths, including regular magnetogram images that map the magnetic field topology across the solar disk. This produces an enormous dataset, years of continuous imagery, time-stamped, paired with a historical record of flare occurrence. A machine learning model, typically a deep convolutional neural network, can be trained on this dataset to learn statistical associations between the patterns in the magnetogram images and the subsequent occurrence of flares of various classes and sizes. The trained models are then evaluated on held-out data, images and outcomes not used during training to assess their prediction skill. Multiple research groups around the world have pursued this approach, and the results are consistently more encouraging than what physics-based models alone achieve for short-term flare prediction. The machine learning models demonstrate measurable improvement over the NOAA probabilistic baseline in tasks like predicting whether an active region will produce an M-class or X-class flare within the next 24 hours. The improvements are not dramatic. The difference between the AI model's forecast skill and the human forecaster's baseline might be expressed as a few percentage points of improvement in detection probability at a fixed false alarm rate, but they are statistically significant, and they have been reproduced across multiple independent studies and datasets. Why do the machine learning models outperform the physics-based approaches in this task? The most likely explanation is that the models are detecting high-dimensional patterns in the magnetogram imagery that human analysts and physical models do not fully capture. The magnetic field structure of an active region is complex enough that the relevant precursor information for flare prediction may be encoded in subtle spatial correlations across the image that are beyond what any manually specified feature extraction captures. Neural networks trained on large enough datasets can potentially identify these patterns without being explicitly told what to look for. The limitation that persists despite these improvements is the fundamental one. The machine learning models improve probabilistic forecasting on hour-to-day timescales. They do not provide deterministic short-term prediction, the capability to say that this specific active region will produce an X-class flare in the next 30 minutes. The improvement is in the statistical characterization of risk, not in the identification of the specific physical threshold that triggers eruption. A model that raises the 24-hour M-class probability estimate from 30% to 42% for a given active region is providing genuinely useful information, but it is still a probability. It is not a forecast of a specific event at a specific time. NASA's partnership with NOAA and with university research programs has been moving machine learning approaches from published research toward operational evaluation. Some AI-enhanced features have been incorporated into the experimental product suite at the Space Weather Prediction Center, where they run alongside the traditional forecast products and their performance is evaluated against outcomes. The transition from experimental to operational status requires demonstrating consistent performance improvement over the baseline across a range of conditions and solar cycle phases, a process that takes time. Hybrid approaches that combine machine learning with physics-based magnetohydrodynamic models represent the next frontier in the field. The concept is to use machine learning to initialize a physics-based simulation from observed data more accurately than traditional data assimilation methods allow, and then let the physics-based model evolve the system forward in time according to the actual governing equations. If this can be made computationally efficient enough for operational use, which is a significant challenge, because magnetohydrodynamic simulations of the solar corona are extremely computationally expensive, it could potentially bridge the gap between statistical pattern recognition and genuine physical understanding of the eruption process. The trajectory of the field is genuinely optimistic. If progress continues at the current rate, the solar flare prediction capability available to mission controllers in 15 to 20 years, the time frame of crewed Mars missions, will be substantially better than what is available today. The combination of better observational assets, larger training datasets, more sophisticated models, and better computational resources is a reasonable basis for expecting meaningful improvements in predictive capability across the 10 to 30-minute warning horizon that would make the biggest operational difference for crew shelter protocols. But that improvement is in the future. For the Artemis II mission launching in 3 days, the state of solar flare prediction is what it is, better than it was 10 years ago, meaningfully improved by AI research that is working its way into operational systems and still fundamentally detection after onset, rather than warning before initiation. Technology is improving visibility. It has not yet delivered certainty, and for the 10-day window that begins 3 days from now, the crew and mission control will be operating with the visibility available today, which is good and detailed, and still insufficient to tell anyone when the active region pointing at the translunar corridor will decide it is ready to fire. Part 13. China and the Silent Moon Race. There is a parallel story to the Artemis II solar weather narrative that receives substantially less attention in the mainstream coverage of the mission, possibly because it is more geopolitically uncomfortable than a story about solar physics, and possibly because it requires engaging with a competitive framing that the diplomatic language of international space cooperation works to soften. But the competitive reality is genuine, it is consequential, and it is one of the reasons that the Artemis II timeline, despite multiple delays, despite hardware challenges, despite the solar maximum timing, has a pressure behind it that goes beyond the scientific and engineering rationale alone. China's space program has been executing a systematic plan of lunar exploration that, placed against the Artemis program timeline with honest assessment, describes a race more accurately than a parallel journey of scientific discovery. The Chang'e program of robotic lunar missions has accomplished a series of progressively more ambitious objectives: orbital reconnaissance, soft landing on the near side, far side landing on terrain no other nation has accessed, and sample return from both the near side and the far side. Each of these missions built operational experience and demonstrated capabilities that directly translate to the next step: crewed lunar surface operations. The China National Space Administration and the China Manned Space Agency have announced plans for a crewed lunar landing before the end of this decade. The stated target destination is the lunar South Pole, a region that has achieved strategic significance in lunar planning for a specific and well-understood reason. The permanently shadowed craters at the lunar South Pole contain confirmed deposits of water ice. That water ice can be processed into hydrogen and oxygen, components of rocket fuel and life support consumables, through electrolysis powered by solar energy collected at the crater rims, where sunlight falls at grazing angles but falls continuously. Water ice at the lunar South Pole is not just a scientific curiosity. It is the key resource that makes a long-term human presence on the Moon potentially self-sustaining, rather than entirely dependent on supply missions from Earth. Whoever establishes physical infrastructure at the most resource-rich South Pole crater rims first will be in an operationally dominant position for the era of sustained lunar presence. The United States has recognized this competitive dynamic explicitly. The Artemis Accords, the bilateral and multilateral agreements that the United States has organized around the Artemis program, now joined by over 40 countries, include provisions about the rights to extract and use space resources and about the establishment of safety zones around operational lunar facilities. The language of these accords reflects a legal and normative framework being built proactively around the expectation of physical infrastructure at specific, valuable lunar locations. The framing is cooperative, but the underlying logic is competitive, establishing the norms before the locations are occupied rather than after. China and Russia are developing a parallel framework. The International Lunar Research Station, which invites partner nations on terms different from the Artemis Accords and reflects a different vision of governance and access for the lunar environment. Multiple countries, particularly in the developing world, have been approached by both frameworks and are making decisions about which to align with. The Moon is becoming an arena where the soft power competition between competing visions of international order is playing out in the language of scientific cooperation and resource access. For Artemis II specifically, the competitive context creates a pressure that has been present throughout the program's extended delay history. Every year that Artemis slips is a year in which China's program continues advancing on its own schedule. The SLS development timeline stretched significantly beyond original projections, with cost overruns and schedule slips that generated congressional criticism and internal NASA scrutiny. The Gateway Lunar Orbital Station, originally planned to be further along by this point in the program, has faced its own schedule challenges. Artemis II, as the first crewed test of the Deep Space Transportation System, validates the investment and demonstrates that the program is real, is functional, and is executing. 4 people going around the Moon without landing is not the mission that wins the South Pole. It is the mission that proves the hardware works, that the crew can operate in the translunar environment, and that the program can proceed to the landing missions that follow. In the geopolitical subtext, it is the United States demonstrating that its crewed deep space capability is operational at a moment when the competing program is advancing toward the same destination. The solar maximum timing creates a genuine physical risk overlay on this geopolitical context. But the geopolitical pressure does not disappear because the Sun is active. The mission proceeds because the reasons for proceeding have not been superseded by the conditions of proceeding. Artemis II is launching into solar maximum, not because NASA is unaware of the solar conditions, but because the balance of reasons, the program objectives, the competitive context, the mission architecture timeline has been evaluated against the risk and found to argue for proceeding. Whether that evaluation is correct is a question that 10 days from now we will know considerably more about. Part 14. The next threat: cosmic radiation beyond the Sun. We have spent most of this conversation focused on the Sun because the Sun is the acute risk for Artemis II, the variable that is elevated, unpredictable, and most directly threatening to the crew during this specific 10-day window. But there is a radiation hazard operating in the background of this mission, and in the foreground of every human spaceflight mission, beyond the magnetosphere that deserves to be understood on its own terms, because it is the problem that will define the limits of human expansion into the solar system and potentially beyond. Galactic cosmic rays are the solar system's permanent background radiation, the unceasing rain of high-energy particles that originates from outside the solar system and permeates the interplanetary medium regardless of solar cycle phase. Their sources include the supernova remnants of massive stars that exploded thousands to millions of years ago, the energetic environments around neutron stars and pulsars, and potentially the acceleration mechanisms of more distant astrophysical phenomena. These particles have been travelling across interstellar space, some of them for millions of years, arriving at Earth's orbital neighbourhood with energies that span an enormous range. From particles that are attenuated by the heliosphere's magnetic structure at the lower end, to particles so energetic that no planetary magnetic field or spacecraft shielding can meaningfully deflect them. The heliosphere, the bubble of solar wind that extends outward from the Sun to the boundary, with interstellar space, many times the orbital distance of Pluto, provides some protection against the lower energy end of the galactic cosmic ray spectrum. The solar wind fills the heliosphere with magnetic field structure that scatters and deflects lower energy cosmic rays, and this effect is stronger during solar maximum when the solar wind is more energetic and the heliospheric field is more complex. Artemis II's solar maximum timing is, in this specific sense, slightly favourable for galactic cosmic ray exposure. The modulated cosmic ray flux during solar maximum is somewhat lower than during solar minimum for the lower energy component. The high-energy end of the galactic cosmic ray spectrum is essentially unaffected by heliospheric modulation, and it is this component that creates the most intractable shielding challenge. Particles at energies of multiple giga-electron-volts and above penetrate spacecraft walls, penetrate human tissue, and when they interact with dense shielding materials, generate secondary particle showers that can increase rather than decrease the biological dose behind the shielding. This is the shielding plateau problem. past a certain shielding thickness, adding more material to stop high-energy cosmic rays produces more secondary particles in the shielding material itself, and the net biological effect on the crew is worse than thinner shielding would have provided. For a 10-day mission, the galactic cosmic ray contribution to total dose is a real but manageable background term. 10 days of unattenuated cosmic ray exposure in the translunar corridor represents a dose increment that mission planners have incorporated into the total dose accounting, and it does not by itself drive the mission out of acceptable range under current standards. The solar energetic particle acute risk is the dominant concern for Artemis II, but for Mars the calculation is qualitatively different. 6 to 9 months of travel to Mars in interplanetary space with no magnetospheric protection accumulates galactic cosmic ray dose at rates that make the 10-day Artemis II exposure look minor by comparison. Radiation physicists estimate that a Mars astronaut would receive roughly 60% of their entire permissible career radiation dose during the transit phases alone, before accounting for time spent on the Martian surface, which itself offers limited atmospheric shielding and no magnetic field protection. The biological consequences of chronic high-energy heavy ion irradiation are among the most poorly characterized areas of space medicine. Heavy ions, carbon, oxygen, neon, iron, and other elements stripped of electrons, traveling at significant fractions of the speed of light, interact with biological tissue in ways qualitatively different from the proton and electron radiation that forms the bulk of the space radiation environment near Earth. A high-energy heavy ion passing through a cell nucleus leaves a track of dense ionization damage, a column of molecular disruption that can produce complex DNA breaks that are harder to repair than the simpler breaks caused by lower energy radiation. The long-term consequences of heavy ion irradiation, cancer risk, neurological effects from particles passing through brain tissue, immune system modulation, are being studied in laboratory settings using particle accelerators to produce analogous radiation fields. The results suggest the biological effectiveness of high-energy heavy ions is substantially higher per unit dose than the effectiveness of photon radiation on which most radiation protection standards are based. The uncertainty in heavy ion biological effectiveness is not a small rounding error. It is a significant factor in the risk calculation for long-duration deep space missions, and it represents a gap in the knowledge base that affects the confidence of risk estimates for Mars missions directly. Until humans actually execute multi-year deep space missions, and the subsequent health outcomes are tracked for decades, the heavy ion biological effectiveness values used in Mars mission risk estimates will remain extrapolated from non-human data and short exposure human studies. Artemis II is the beginning of filling that gap. The crew's dosimetry data, the biological samples that will be taken before, during, and after the mission, the health monitoring that will continue for years after their return, all of it contributes to the empirical foundation that the next generation of deep space missions will build on. The 10-day Artemis II transit is the first entry in a dataset that needs hundreds of entries before the statistical power becomes adequate for the questions being asked. Solar storms are the acute risk that defines the Artemis II mission window. Galactic cosmic rays are the chronic constraint that defines the Mars mission architecture. Both are consequences of leaving the magnetosphere, the same protective field whose absence is the defining physical feature of everything we call deep space. The sun's particle storms are just the beginning of the radiation complexity that awaits human beings who want to live and work in the space between the planets. Part 15. The real question isn't if, it's when. We have been building toward a single honest reckoning with what the numbers actually mean for the Artemis II mission, and now we are here. Not to alarm beyond what the evidence warrants, there is enough of that in the world, but to be precise about what is known, what is uncertain, and what the crew is actually facing when the launch vehicle clears the tower in 3 days. Solar storms are not a hypothetical risk. They are an inevitable feature of the environment that any human being enters when they leave the magnetosphere. The sun produces solar energetic particle events because it is a magnetically active star with a complex internal dynamo generating cycles of energy build-up and release. It has been doing this for 4.5 billion years. The physics that produces the events has not changed. It will not change for another several billion years until the sun exhausts its hydrogen supply and begins its terminal evolutionary phase. Any mission that places human beings in the translunar corridor or beyond for any duration of time is operating in an environment where major solar energetic particle events are a permanent background possibility. The question has always been, and can only ever be, whether the timing of a given mission intersects with the timing of a given event. Timing is the variable that engineering cannot control. The Orion capsule can be built with the best practical shielding. The storm shelter can be optimized for available mass and volume. The monitoring systems can be the most sophisticated ever deployed on a crewed mission. The crew can be the most thoroughly trained in radiation event response of any crew in spaceflight history. None of that changes when the sun decides to fire. The engineering manages the consequences, it does not manage the calendar. The probabilistic reality of Artemis II is this. NASA has evaluated the risk of a mission-threatening solar event during the 10-day mission window, using the best available models and the current solar observations, and has determined that the probability falls within the range accepted for human spaceflight. That is not a casual determination. It represents the output of a serious, technically intensive risk assessment process conducted by people who understand the physics and take the stakes seriously. The mission has been approved for flight, but that risk assessment was built around models that, for this specific solar cycle, have already been demonstrated to underestimate activity by approximately 70% in terms of sunspot output. The active region complex producing multiple events per week from a geo-effective position was not a modelled scenario that influenced the initial mission risk numbers. It is the actual observable current state of the Sun. The probability that NOAA and NASA now assign to encountering a significant solar particle event during the 10-day window is higher than it was when the initial risk assessment was completed, because the solar conditions are worse than the planning baseline assumed. How much higher? The honest answer is that precise quantification at this point depends on assumptions about event probability rates during the specific active region's productive phase, on the trajectory geometry, on whether the region maintains its current activity level or decays, and on how the interplanetary particle transport conditions evolve during the mission. The uncertainty in that calculation is substantial. What is not uncertain is the direction. Current conditions are more hazardous than the baseline planning assumed, and the magnitude of that hazard elevation is meaningful. The unanswered questions in this story deserve to be named plainly. What happens during a peak solar eruption while the crew is at maximum distance from Earth, during the transit phase rather than during approach or departure? What is the actual dose delivered by a major SEP event to occupants of the Orion storm shelter configuration as a function of event intensity? How close is the acceptable risk threshold to the estimated probability distribution of events during this launch window? These are not questions being asked rhetorically. They are open questions in the planning documents, in the risk assessment literature, and in the minds of the people responsible for the crew's safety. For 50 years, humanity's presence in space has been almost entirely inside the magnetosphere. 50 years of ISS crew members, shuttle astronauts, station residents, laboratory workers, and explorers, all of them operating inside the invisible electromagnetic shield that Earth's molten core generates continuously, that has been deflecting solar wind from this planetary surface since long before the first multicellular organism drew breath in the Precambrian ocean. We did not choose that protection. We were born into it. We evolved inside it. Every biological mechanism we have developed over billions of years of life on this planet developed in an environment where the magnetosphere was a constant background feature. 3 days from now, 4 human beings will step outside that background. They will launch from a planet wrapped in protection and enter a space where that protection ends. They know this. They know it in more technical detail than any astronauts in history, because the monitoring systems, the research literature, and the protocols that define their mission have been developed with precisely this knowledge in mind. They are not going in ignorance. They're going in full awareness of what the translunar corridor is, what solar cycle 25 is doing, what the active region on the solar disk is capable of, and what the shelter can and cannot protect them from. That awareness is, in its own way, the most remarkable thing about this mission. Not the engineering, not the rocket, not the trajectory. The fact that 4 people, knowing exactly what waits for them outside the magnetosphere, knowing that the sun is running hotter than the models predicted, knowing that there is no early return option, knowing that if the timing is wrong there is nowhere to hide, have decided that going is worth the risk of going. That the things we might learn, and the places we might eventually reach, and the future we might build for everyone who comes after them, are worth the 10 days of exposure to an indifferent star doing what it has always done. Humanity is not entering space blindly. We are entering it knowing exactly what we are leaving behind. The protection that Earth's core has been generating for us since before we existed, the shield we never had to think about or earn or build, we are walking away from it on purpose, with open eyes, because the universe does not rearrange itself to fit around our comfort. The sun will do what it does, the crew will do what they trained to do, and in 10 days we will know something we did not know before about what happens to human beings when they leave the only protective field our species has ever known. That is not a small thing. It is the beginning of a much longer story. And the question of whether we are ready to tell it, whether our engineering, our medicine, our forecasting and our courage are adequate for the chapters that follow Artemis II, is a question that will take decades to fully answer. The window is open, the countdown is running, and the sun, 93 million miles away, is doing exactly what it was doing long before any of us were here to watch it.